and where mod of t1 minus t2 is smaller than eta. So when mod of t1 minus t2 is greater than equal to eta, it is r t1 comma t2 is equal to lambda square, and otherwise it's lambda square plus lambda by eta minus lambda t1 minus t2 upon eta square. Autocovariance. Autocovariance C of t1 comma t2 is equal to 0 lambda by eta lambda into t1 minus t2 upon eta square for t1 minus t2 smaller than eta, and for t1 minus t2 greater than equal to eta, it's equal to 0. The Poisson increment process is introduced to prepare us to define the Poisson impulse process. One way to define it is interesting to see that the expression of autocorrelation lambda by eta minus lambda t1 minus t2 upon eta square for t1 minus t2 is smaller than eta is a triangle with lambda where lambda is independent of eta, where eta goes to 0. If lambda goes to 0, the triangle becomes impulse with area lambda. The third point impulse process. The point impulse process is defined as z of t is equal to d x eta upon dt, where x eta is x of t is a Poisson process. X of t. So z of t, the graph of z of t goes like this. The probability mass function has no definition. The mean of z of t is equal to the mean of point impulse function, that is equal to e of z of t is equal to lambda. The autocorrelation of r t1 comma t2 is equal to lambda plus lambda of impulse function of t1 minus t2. Autocovariance is equal to c of t1 comma t2 is equal to lambda of impulse function of t1 minus t2. The process z of t minus lambda has zero mean, and z of t minus lambda is equal to white noise. In the real world, there are some short noises as is given in the figure. This semi-random telegraph signal. Semi-random telegraph signal is defined as the Poisson points. Again, the number n t1 comma t2 of point ti in the interval t1 comma t2 of length t is equal to t2 minus t1 is a Poisson random process. It's a Poisson random variable with parameters lambda t. Where probability of n given n of t1 comma t2 is equal to k is equal to e to the power minus lambda t into lambda t to the power k upon k factorial. X of t is equal to 1 if k is even in 0 to t, and minus 1 if k is odd in 0 to t. The first order probability mass function is equal to probability of x of t is equal to 1 is equal to e to the power minus lambda t into e to the power lambda t plus e to the power minus lambda t divided by 2, where probability of x of t is equal to minus 1 is equal to e to the power minus lambda t into e to the power lambda t minus e to the power lambda t divided by 2. Mean. The mean of the function is e to the power expectation value of x of t is equal to e to the power minus lambda minus e to the power minus 2 lambda t. Autocorrelation is r of t1 comma t2 is equal to e to the power minus 2 lambda t1 minus t2. Autocovariance c of t1 comma t2 is equal to e to the power minus 2 lambda t1 minus t2 into e to the power minus 2 lambda t1 plus t2. Probability of x of t is equal to 1 is not 1 by 2 because we start it with plus 1. Probability of x of t equal to 1 should be a little higher than 1 by 2. Probability of x of t equal to 1 is equal to e to the power minus lambda t e to the power lambda t plus e to the power minus lambda t upon 2 is equal to 1 upon e to the power minus 2 lambda t divided by 2 goes to 1 by 2 when t goes to infinity, which matches our expectation, is equal to e to the power minus 2 lambda t goes to 0 when t goes to infinity, which matches our expectation as well. The autocorrelation is equal to r of t1 comma t2 is equal to e to the power minus 2 lambda t1 minus t2 goes to 0 when t1 minus t2 goes to infinity and t1 minus t2 goes to infinity. random telegraph signal. The random telegraph signal y of t is y of t minus e of xt minus 1 e of xt, comma probability of a is equal to 1 is equal to probability of a is equal to minus 1 is equal to 1 by 2, where xt is a semi-random telegraph signal. The first order probability mass function for random telegraph signal is equal to 1 by a probability of y of t equal to 1 is equal to probability of y of t equal to minus 1 is equal to 1 by 2. The mean is equal to expectation of x of t is equal to 0. Autocorrelation r of t1 comma t2 is equal to e to the power minus 2 lambda t1 minus t2. Autocovariance is equal to c of t1 comma t2 is equal to e to the power minus 2 lambda t1 comma t2. Probability of y of t equal to 1 is equal to probability of y of t equal to minus 1 equal to 1 by 2. This makes us guess that probability of y of t may be strict severe stationary. Random walk. Toss a fair coin n times. K is the number of heads in n tosses. So x of nt is x of nt minus k of ks minus n minus k into s is equal to 2k minus s minus n into s. Probability of x of t is equal to x of nt is equal to rs. Condition from where n taken from where n plus r by 2 taken from n into 1 by 2n for small t that is greater than equal to n of capital T that is smaller than n plus 1 into capital T, where mean is equal to e to power expectation of x of t is equal to 0, and autocorrelation function is equal to r of t1 comma t2 is equal to x of t1 x of t2 is equal to expectation of n of t into expectation of m of t is equal to minimum of n of m into s square. Autocovariance is equal to c of t1 comma t2 is equal to estimation value of x of t1 into x of t2, that is equal to estimated value of x of nt into estimated value of x of mt is equal to minimum of n of minimum of n comma m whole square. From probability mass function, we guess that when n goes to infinity, we will have the Gaussian density. The autocorrelation function contains a term minimum of t1 comma t2, which comes from the property of independent increments. Wiener process or Brownian motion. Wiener process wt is equal to limit of xt limit t tends to infinity and s square by t tends to 0